Hello there. Let's talk about how plate tectonics makes mountains, crustal deformation, and mountain building. Like almost all active volcanoes, mountains are built along or near plate boundaries. This lesson will focus on non-volcanic mountains, like those we see here in the photograph, which offers us a great example of folded mountains. These form where the crust has been bent or folded upwards by tectonic stresses to create a mountain range. Here are our big picture learning objectives. Identify the types of deformation and stresses that deform rock. Summarize the geologic processes that form each of the four types of mountains. Identify and interpret geologic structures in illustrations, block diagrams, and geologic maps. The geologically young mountains, those less than 100 million years old, are found along the margins of the continents surrounding the Pacific Ocean and along the east-west trending line through southern Asia and Europe. Our mountains made. In order to answer this question, let's consider a chain of events that can result in making a mountain. Deforming the crust means changing the shape of a body of rock by bending and or breaking it. This happens when stresses are applied to rock, which typically happens along or near plate boundaries. Over time, stresses deform the crust into geologic structures like faults and folds. Through movement along faults and or the bending of rock underground, the crust can be pushed upwards to make mountains. Mountains are also made through volcanic activity, as we have recently discussed. We recognize four main types of mountains on Earth: folded, fault block, volcanic, and granitic batholith, or batholith mountains for short. So why does rock deform? Rocks deform because stresses act on them. A stress or stresses are forces that push or pull or tear a body of rock. Earth scientists recognize three types of stresses: compressional stress, tensional stress, and shear stress. Compressional stress causes a body of rock to be squeezed. This mostly happens along convergent plate boundaries. Tensional stress pulls a body of rock apart in opposite directions. This would most be associated with divergent plate boundaries. Shear stress is a bit like tearing, where one body of rock is moved horizontally past another in opposite directions. This happens along transform boundaries or transform faults. So why all the stress? The rock making up Earth's crust is stressed out because of plate tectonics, the interaction of the plates along plate boundaries. Convergent, we're going to have mostly the compressional stress. Divergent, tensional, transform, shear. Stresses cause deformation to a body of rock, which changes its shape through bending, through plastic or elastic deformation, and breaking, known as brittle deformation. Bending and breaking change the geometry of the rock of the crust, making geologic structures. Deformation makes geologic structures which include folds and faults, where the rock has been bent or broken. How do we know that a body of rock has been bent? Well, let's start with locations where we can actually see rock above ground. Such localities are called outcrops. Chances are the outcrop will be sedimentary rock, which makes up approximately 75% of all the rock exposed on Earth's surface. As you might recall, sedimentary rock originates in horizontal layers, known as strata. Considering this fact, we can use the horizontal strata of sedimentary rock as our reference, or baseline. If we observe rock that is no longer horizontal, we know that it has been subjected to some degree of deformation. We see more examples of that here, where the rock has been bent into the folds that we see in these photographs. There are two main types of folds, anticlines and synclines. Anticlines when the rock has been folded upwards. Think of a rainbow. Syncline where the rock has been folded downwards. Think of a broad U. Anticlines and synclines often occur together. Think of pushing a rug into a wall. It would fold both upwards and downwards. Here's an example of an anticline in a drawing. Here's an anticline in real life. You can see the strata bent upwards. Here are a couple of synclines and another one here. The basic types of folds. Here we see the progression of horizontal strata being deformed by compression into anticlines and synclines. So we would start here with a sequence of horizontal strata that's then deformed into the anticline and syncline we looked at earlier, followed by erosion, which exposes the limbs or the layers of strata that have been folded. Strata more resistant to erosion may stand out topographically as an outcrop. The hinge, the term you see here with the dashed lines, refers to an imaginary line around which the strata has been folded. When the strata has been bent around a tilting or non-horizontal fold axis or hinge line, a plunging fold is created. The folds we looked at in the previous illustrations were examples of symmetrical folds like these. Symmetric folds are those that have the same tilt on either side of the fold axis. In other words, the strata on opposite sides of the fold axis, or axial plane as it is also called, are mirror images of one another. On the other hand, we can have asymmetric folds. This occurs when the fold axis itself has been tilted from vertical, and now the limbs of the fold on opposite side are not tilted in the same way. Let's move on to structures caused by brittle deformation, known as faults. Faults are breaks in the crust along which movement has occurred. When this happens, we get earthquakes. We recognize two categories of faults, dip-slip faults and strike-slip faults. There are two types of dip-slip faults, normal faults caused by tensional stress, reverse faults caused by compression. For strike-slip faults, we give them two names, right-lateral or left-lateral, both of which are caused by shear stress. In the photograph here, we have an example of a dip-slip fault. In order to give a dip-slip fault its name, we need to consider which side of the fault is the hanging wall and the footwall. The hanging wall block of rock is the block of rock that is resting on top of the fault plane. It is the block above the fault, as opposed to the footwall block, which is below the fault plane. Let's look at it another way here. So this guy here is looking at an outcrop with a fault, which is in dashed red there. The block of rock above the fault is the hanging wall. The block of rock below the fault is the footwall. Vertical faults, or dip-slip faults as they are also called. Let's talk about normal faults first. These exist where the hanging wall moves down. So, something like that. These occur where there is extension or stretching of the crust, which is caused by tensional stress. And again, this tensional stress will result in the hanging wall block moving downwards along the fault plane. Here's an illustration of a normal fault. The hanging wall block, which used to be up here, imagine the ground surface extended continually across the block diagram here. Then there was movement along the fault due to tensional stress. The hanging wall block slid downwards along the fault plane, exposing the fault scarp. The fault scarp is a term that we give when the fault has just moved and the fault surface is exposed. We call that the scarp. This person is standing on the hanging wall, which slid downwards relative to the footwall. Here's another example of a scarp. This is from the earthquake that happened last year that you guys might remember. Gentleman here is standing on the footwall. The woman is on the hanging wall, which slid downwards along the fault surface. Reverse faults are the opposite of normal faults. This is when the hanging wall block moves upwards along the fault plane. And these are always the result of compressional stress. We call it a reverse fault when the fault surface is fairly steeply inclined, as it is in the way I've drawn it here. If the fault surface is less steep, then we call it a thrust fault. But in either case, the hanging wall slides upwards along the fault plane. Let's take a look at that here. So again, imagine that this yellow strata was at one time connected. Compressional stress caused the hanging wall block to slide upwards along the footwall. The slippage would happen a few feet at a time, but with enough slippage and enough earthquakes and enough time, you can build up a mountain. Here's a photograph of a small reverse fault here, where the hanging wall block has slipped or slid up over the footwall block. This could be the result of one fairly large earthquake or perhaps several smaller ones. Strike-slip faults are different than the dip-slip or vertical faults in that the movement is horizontal or lateral along the fault plane. These are always the result of shear stress, and we recognize two types, right-lateral or left-lateral. The difference being is how objects on the other side of the fault appear to move relative to you. The most famous right-lateral strike-slip fault would be the San Andreas fault here in California. That's the fault that is supposed to give us the big one, which we are overdue for. Left lateral are the opposite of the right lateral, in that the movement of objects on the other side of the fault appear to be to the left. Let's take a closer look at this. So here we have a right lateral strike slip fault taken, the photograph taken from an airplane flying above. The white strata here used to be connected to the white strata over here. But after many earthquakes, this sequence of white strata has been shifted considerably over in this direction. If you were to be standing here looking across the fault, you would have to look to your right to see the strata that was once connected to this strata. Similarly, if you were standing here looking this way, you again would have to look to the right to see the offset strata. Now, a question we need to ask ourselves is if the structures are below ground and out of sight, how do we know they're there? And the answer is that we make a geologic map. A simplified version of a geologic map. You'll notice all the bands of color. Each band of color represents a distinct geologic unit. In other words, different sequences of sedimentary strata. One layer might be a sandstone, another layer might be a conglomerate, another layer might be a shale, etc. The line that separates one unit from another is known as a contact or geologic contact. So how would you put something like this together? This is actually a very important skill that you would learn if you became a geology major and a geologist. Making a geologic map so you can discern the structure of the strata beneath the surface requires you to measure the orientation of the strata. This is done by taking strike and dip measurements. Strike is the orientation of strata relative to north. We define the strike as the line of intersection created when the strata intersects a horizontal surface. In this case, the horizontal surface is being depicted by a lake. The surface of a lake, of course, would be horizontal. So as the strata pokes out of the water, the contact line between the strata and the lake surface is our line of strike, which would be measured relative to north. In this case, here's north. The line of strike is 38 degrees to the east of north, or north 38 degrees east. The amount of tilt of the strata is known as the dip, and this is measured just as you would measure the angle in a math class. Here the tilt is 55 degrees from horizontal. That gives us our strike and dip. Here's a photograph of a similar situation in real life. You can see the strata sticking out of the lake surface, this outcrop here. It is dipping into the water, and the line of intersection between the strata and the lake surface is our strike. So that's our strike, and that's our dip. By measuring strike and dips on the Earth's surface, we can determine what's going on beneath the Earth's surface. And in this way, we can make something called a block diagram. So here's our strike and dip symbol. Our line of strike is going this way. You can see the contacts between this strata and the other strata, indicating that the strike is going like that, and then the dip is this way, The dip is 35 degrees in that direction, which would be to the west. At the bottom here, we have some important symbols that are also discussed in your textbooks. By collecting strike and dip measurements on the Earth's surface and marking where the contacts are between one geologic unit and another, a geologic map can be made. So imagine, if you will, if you were to walk across the Earth's surface here. If you had some training in geology, as you are gaining in this class, you don't need much more than what you're learning here in this lecture and what you'll be learning to do in the lab. Walking across your surface, you might be able to identify the rock that you're walking across. In this case, this would be a shale unit. And then, being the keen observer that you are, when you get to about here, you would recognize that the rock type changes. Maybe the color is different, maybe the texture is different, and certainly this outcrop is sticking out higher out of the ground, topographically higher. So now you have a sandstone upon which you take a strike and dip measurement, and you mark that on your map. Continue walking, you recognize that, hey, again, the rock type has changed. Maybe you're carrying with you some acid, which you drop on the rock. It reacts with the rock, and you realize, hey, that's a limestone. You can continue to walk, and then you recognize there's a change in rock again. Hey, wait a second. This is the same sandstone I saw back over there, but the orientation of it is different. Now it is having the same strike, but a dip of 85 degrees in the opposite direction, off to the east. Walk a little further. Wait a second. Here's that shale again. You walk across the shale. You encounter the same sandstone again. You take another strike and dip measurement and realize the dip is now tilting in the opposite direction once again. You walk a little further. There's the limestone again. What could cause such a pattern? The answer would be a syncline and anticline. So in this way, by taking strike and dip measurements, we can create a geologic map, which in turn allows us to create a block diagram and visualize what's happening beneath the Earth's surface. You're going to be learning more about this through your reading and the laboratory activities. Good luck.